Hi everybody, I hope you're doing well. Let us continue our previous lecture where we just identified what is the action of the operators, the psi dagger and psi. They are creation and annihilation operators in position space, okay? So they are operators. But we didn't discuss yet how to quantize operators. All right, so in first quantization, if you want to calculate the average of a given operator, suppose the Hamiltonian, which is it could be any other operator, you just calculate it given a ket state. So you put the operator in the middle of your, let me say, your sandwich, and you calculate this bracketed expression, and you'll find out a scalar, a number here. In the case of Hermitian operators, it will be a real scalar number. And for Hamiltonian, of course, it is the energy. So what does that mean in second quantized version? So what is the version for the Hamiltonian in the second quantization procedure? Okay, so let me bring you a general recipe, and we will discuss the form of the Hamiltonian. I will use the case of electrons, but it could be for bosons, for some bosons, and it will work just how fine if you have to second quantize a given operator. So suppose you have the first situation, first case corresponds to a single particle operator. Okay, so single particle operators. Okay, so they are acting on a given point of space. They do not connect to separate points, or they perhaps they are not functions of positions of more than one particle. All right, so single particle operators, I will write it as H1 in a first quantized version if you have a non-relativistic particle. So suppose a non-relativistic particle under the influence of an external potential, okay? A potential given by other types of particles, all right? So suppose that it's given. So under external potential energy or external potentials, you have your Hamiltonian for first quantization in the following form. Okay, you'll have a p squared divided by twice the mass plus, which is an operator in first quantization, plus some operator depending on position. All right, so this is also an operator, and therefore this is operator. This is an operator, and you have for this Hamiltonian, you have in first quantization, you have that the momentum operator will be given by minus I h bar, the nabla operator, okay? And if you are trying to solve this, you will find some set of eigenstates of energy, so some energy eigenstates. I will call them E states. So the eigenvalue E times the state E, all right? Of course, you could project out these energy eigenstates into the position basis or momentum basis or whatever. But of course, if in the case, a particular case, U of R is equal to 0 for free particles. So free particles, you would have the following. H1 applied to some given energy eigenstate is equal to energy eigenvalue times the eigenvector, the eigenstate, and this energy is depending on the momentum value. It is a momentum eigenstate, so this energy, it will be just p squared divided by twice the mass, and your energy eigenstate is just a momentum eigenstate for free particles. All right, so this is in the first quantization. What is the recipe for doing a second quantization? It could be this form of the Hamiltonian in general. Okay, you would have the eigenfunction. So suppose you have for a given energy the energy projected out onto a position basis. You call this a phi function with a given momentum, or perhaps some another quantum number, some alpha here. In this case, momentum for free particles, but it could be atomic orbitals or whatever. Okay, so some set of quantum numbers alpha. It depends on the position. Okay, and this, of course, satisfies time independent Schrodinger equation using this form of the operator in first quantization. So let us quantize the Hamiltonian for a many body problem, for a large number of particles. What we need to do? Now see that your Hamiltonian, which is the H1, when represented in position basis, will produce some energy times that eigenfunction, and this is just minus h bar squared, the Laplacian here divided by twice the mass, apply it to phi of r, plus the potential energy times the eigenfunction is equal to the energy given a set of quantum numbers here, and times the eigenfunction. Okay, so this is the first quantization. Notice here that in no place we have mentioned any other particle. Okay, this is a solution for the problem for a given particle at the position r. But in many particles or in many body problems, you will have many particles. So if you try to solve that using second quantized methods, okay, there are other possible methods, okay, but for second quantized methods, if you are trying to solve a problem with many body or many particles, a large number of particles, the recipe is the following. In replacement of the average, which in the first quantization would read the following, you would plug in here the Hamiltonian for a single particle. We are not dealing with the interactions within between particles. Okay, we are just considering for now a single particle. So suppose there are electrons, they can be subjected to the potential of protons, but there is a single electron, and I am writing the Hamiltonian for this electron here, okay? And the proton produces the potential energy. So this is external. It's provided by something else, okay? So we are dealing with the electrons here for the sake of simplicity, but you could be trying to solve a problem for a given type of particle, okay? So in this case, when you consider a single particle Hamiltonian and you try to calculate the energy average, what you do is given a state, and a given state would be represented as a summation of orbitals. Okay, I'll represent these orbitals in the following way. Okay, they are energy eigenstates, and there are coefficients here. So suppose there are some psi of alpha. Let me write this as a coefficient c. Okay, so some c alphas here, summed over all the alphas. What you need to do here is, suppose you introduce in first quantization, we are dealing with first quantization here. You introduce the unity or the resolution of the identity here, the identity matrix. Sorry, and this identity matrix, I can rewrite it in a form of a position basis. So in d dimensions, suppose 3 dimensions, you need to integrate over the volume. So in 3 dimensions is a 3-dimension integral, so dx, dy, dz. Okay, so d3r is dx, dy, dz. And we will insert our position basis here, completeness. All right, this is the completeness. Summation over all the exterior products of position cats and times the psi which is already there. Okay, so this is the wave function calculated at some position r. At a given instant of time, I will omit time here. I will be omitting the time variable, but suppose there is evolves in time. So this, okay, let us rewrite this as a function of time. This psi here, this function can be a function of time, all right? So this is a function of time. A given state can be expanded given a complete basis. So if you have, for completeness, for the sake of completeness here, if you have two distinct states, alpha and beta, you have a Kronecker delta or a Dirac delta if this alpha and beta are continuous indices. And of course, the summation of phi alpha with the phi alpha multiplied in the external product over all the alphas, which satisfy the set of quantum numbers which make possible to satisfy a single particle Hamiltonian. Of course, this is the identity, okay? So this is the identity matrix. All right, this is a complete basis. And I can expand a given psi, a given state, uh, in a given basis. So the basis can span all the vector space of functions. All right. This way, we already know that this Hamiltonian, we already know the procedure. You could insert here the basis of the Hamiltonian or another completeness here. Okay, you could write it as another completeness, but I will skip some of the calculations. You could do that. Okay, and in this way, some psi times h1 times a psi, this average here. You could plug in here any other operator, okay? So I am more concerned about the Hamiltonian because it's more important. But it could be angular momentum operator, spin operator, or whatever. Whatever the operator you are trying to calculate here. It could be a charge operator, current operator, whatever, right? So the only restriction here is it is acting on a single particle, a position and momentum operator of a single particle, right? This is the only restriction here. I am anticipating here, but what would be the Hamiltonian term of the operator term for a two particle? Suppose you have an operator which depends not only on the position of a one particle, but in position of a second particle. It could be depending on momentum of other particles. So this, depending on position of two particles, is a second order operator. Okay, so this would be the case. So suppose the electrostatic energy between two electrons would be given by the following: minus plus E squared, the electric charge squared, divided by 4 pi epsilon. The epsilon is the electric permittivity of vacuum, all right? And it depends on the distance. So this is the electrostatic energy potential, okay? This would depend on the position of two particles. We will deal with it a, a little bit later in this lecture, okay? So this is an example. It depends on the position of two particles of the same kind, okay? Because of course, the potential of the electron under the presence of the ions of the nucleus, of course, is of the form minus some atomic number here, E squared divided by 4 pi epsilon 0, the distance of the electron minus the position of the ion, but you could put the ion at the position 0, so this just depends for the ion, the electron ion potential. It just depends on the position of the electron. Supposing the ion is non-moving, it is static at the center of your coordinate system. But here, if you have two electrons interact, and this is what we are calling a two-particle Hamiltonian, because the two electrons are of the same type. They are identical particles. Okay, so single particle, two particle, three particle, and so on and so forth, you define for the same kind of particle, for identical particles. So for a given electron, positions of ions, it doesn't matter because the ions are other kinds of particles. They are not identical to the electron. But one electron is identical to the other. So this is a two particle operator. It operates on the first electron, these are one, and these are two operates on the second electron position. And they are identical. You can exchange them. For if you would have an ion at the position R, the capital R here, this ion here is not the same as the electron. So the operator for electrons acts on a single electron. Okay, so this is the distinction for a single particle operator and a two particle operator. But let us continue here. So in this case, I can just operate this, represent this operator in the basis of position, and we'll produce something, and we would have something like this. For you could show that, but you could have something like this: a psi complex conjugated or transposed conjugated if it is a spinor. Okay, so to be precise, a transpose conjugated here, when you project out the psi onto R, this is an operator depending on position. So this is the Hamiltonian of a single particle. It could be another operator, as I previously mentioned. And this is the psi of R, okay? So notice the following. Our psi of R is just in first quantization, the projection of our ket state onto the basis of position. Of course, this is the transpose conjugated of this object here, but this is just something like the summation over alpha, the C alpha, which is a complex number here. This is just a complex number times a phi of alpha depending on the position and time. Perhaps you could introduce the time dependence into the basis functions, okay? Or you could introduce in the operators, what you prefer. doesn't matter here, but it is just projecting out this state here. So you have the R projected here. This is a complex number. You will project out this thing here, and this is a function depending on position and time. Of course, as I said, you could plug in the time dependence here or the time dependence in the coefficients. Okay, it doesn't matter. You could do both ways. Okay, it's just a method of separation of variables. You could separate the variables whatever do you want. Okay, so you could just consider that these coefficients are complex numbers, but they evolve in time. All right. So this is your operator. This is your wave function expanded in the position basis. Okay, they depend, of course, in space-time coordinates. All right, and this thing here, is what is written in this line here. So this produces a number. All right, or if your operator, because the Hamiltonian is a scalar in classical mechanics, it produces a number. But if you plug in here momentum, it is a vector. It will be a vector here, and the result will be a vector. The average in the x direction, the average in the y direction, the average in the z direction. So it works for anything, provided this is an operator in quantum mechanics in the first quantization procedures. Okay. Well, notice that when you multiply psi dagger by Hamiltonian by psi, remember that psi squared, which is something like psi dagger psi in the first quantization, it is a probability density. And it is measured in units of meters to the -3 in 3 dimensions. So 1 over volume. It is the inverse of volume in units of the international system. Therefore, if you multiply psi dagger by the Hamiltonian by psi, dimensionally speaking, this corresponds to some Hamiltonian density, which I will call H1, corresponding to a psi dagger of a given position and function of time. Of course, this is a function of time here also, all right? And times the operator in first quantized version here times psi of r and t. Notice that this has units of energy. If you are measuring the Hamiltonian in joules, it will be joules per cubic meter, or if you're measuring the Hamiltonian in electron volts, it will be electron volts divided by cubic meters. Okay, so this is the unity of this object here. And when you integrate out over a volume in 3 dimensions, the volume is cubic meters, it cancels out this cubic meter here, and you'll find out just electron volts, because the average of an energy operator, it will be energy. So whatever the operator is here, you plug in some operator here, any operator, you'll find out for any given operator. So suppose psi and operator psi, you will be the same. It could be a vector operator. You will be the same expression, replacing the Hamiltonian by a given operator. So we'll have a psi dagger of r and t, and the operator given. Just the only restriction, it acts only on the coordinates or momentum or whatever on the coordinates of a single particle. So this is the one. Therefore, this one is the index. Just to remember you, it acts on the on the coordinates, on the quantum numbers of a single particle. All right. So if you have any given operator, it could be a vector operator, it could be anything. This operator here, this quantity here, would be measuring units of O1 divided by cubic meters, or whatever the units of your system of units, of physical units, okay? So, but in this case, we are interested in the Hamiltonian because it's usually the most important. But it could be electric current here. It could be charge here. It could be angular momentum. It could be spin, magnetic momentum, whatever, okay? And this thing here is called the Hamiltonian, in this case, the Hamiltonian density. Okay, so this is a Hamiltonian density. And this object here would be the operator density. So charge, electric charge, suppose this O1 here is some operator counting the electric charges. So this would be an electric charge density. This object here is electric charge density. If it's electric current, it will be a density, all right? If you have whatever you have, this would be a density of that operator, okay? So this is the Hamiltonian density. But it's first quantization. This is just a number. What we need to do for second quantize it, so let me just erase this part here. So for second quantization, what we need to do? Second quantize it. You need to replace your objects, which are functions, by operators, which corresponds to replacing, of course, the dagger also, which corresponds to replacing these coefficients, which are just complex numbers, by operators. Now they are annihilation operators. And the result of this will become an operator, because you do not have anymore a number. You will have here the following, which is called a second quantized version of the Hamiltonian. It's another Hamiltonian. Okay, this Hamiltonian is just another operator, which is an integral over d3r psi dagger, which is now an operator. So this produces a matrix. All right, it's not an energy, a single energy value anymore, which is the average of the Hamiltonian, in the case of the Hamiltonian, okay? It is a matrix, so a matrix is another operator, and this corresponds to the second quantized version of your Hamiltonian. And you'll see what will be produced when we calculate things. So you pick the first quantized version of your Hamiltonian here, all right? You pick up the first quantized version of your Hamiltonian here, and this is just differential operators usually, and you apply it to this, converting these things into operators, whatever the operator is. So another given operator would be operator here, integral d3r, or how many dimensions do you have? So 2 dimensions is an area integration, or if it's 1 dimension, this is just the integration over dx, for instance, and you have these things here, right? In this way, you just convert functions into operators by converting them into annihilation operators. So this object here, which is a complex number, now becomes a annihilation operator which annihilates a particle in the state alpha. Okay. Of course, if you have a psi dagger, it will create a particle in the state dagger. Okay. This is it. Just remember that this basis here is complete. Okay. This is a complete basis. So let us just work out what happens in this scenario here. Just remember the Hamiltonian applied in the first quantization, applied to a state phi of alpha, just produces the energy E alpha times phi of alpha. Okay, so this is what is produced by this Hamiltonian. And we can use here plane waves. I will specify plane waves in what follows. But for now, let us just consider this thing here. Okay. And our Hamiltonian here will be in second. So this is first quantization. This is an eigenvalue equation. An eigenvalue equation just for us to find out a complete basis. So from this we find a complete basis. And our operators will be expanded in terms of that thing. So our psi dagger of R and T times the H1, a psi of R and T, okay, will be written, this is now an operator, will be written in the following way. So integral over d3r, okay. I am writing this as an operator, so I will have a summation over all the states alpha, phi dagger of alpha on the position r at time t. This is summation over alpha. And here I will have a C dagger of alpha. Okay, so this is the expansion of this thing. It will be a complex number, but since I am dealing with the second quantized version, I am converting this, which would be a function in first quantization, to an operator in second quantization. And this operator here, the Hamiltonian, continues here. Okay, and we will expand the second, this operator here, which is annihilation operator, into the same set, the same complete basis, but since they are dummy indices, they are being summed over. I will use another beta here. So this beta is the C of beta times phi beta of R. And I can plug in the time dependence here or in the functions. Okay, so whatever do you choose. And in this way, our Hamiltonian applied to the state is just an eigenvalue equation. This produces the following: an integral over d3r over the entire volume, okay, a summation over both indices. This can be a set of quantum numbers. So for instance, if you are using plane waves, you need to specify the momentum and spin. So alpha, in a particular case, plane waves, these alphas are momentum and spin, okay? The betas, you need to use a p primed and sigma primed, okay? So for plane waves. But what you would find a C alpha dagger. Remember, I am using two distinct labels, but it is the same basis. So it's C beta, they are operators. I am plugging in the hats here, just remember you, they are operators. If first quantized version, they would be just complex numbers whose modulus squared would correspond to the probabilities or the amplitude, the no, the probabilities of finding the state at a given alpha. Okay, so in first quantization, a C alpha squared, in first quantization, they would correspond to probabilities of finding the system, the particle in the state alpha. In the second quantized version, they are operators. They are no longer probability amplitudes. Okay, they are operators which create a particle at a given state or annihilate a particle at a given state. So this annihilates in the state beta. This creates a particle in the state alpha. Okay, so we have phi dagger alpha of R and T. We could just bring the time dependence to these operators. It will be no problem in that. Okay, times the energy of the state beta, because when you apply the H1 to the phi beta, it's just the energy eigenvalue equation. So it produces the energy of the state beta because it's applied to the right. Okay, I am applying this operator to this wave function here, and when we apply this H1, it is a first quantized operator, so it operates on the wave functions, which are, it's better to use, which are his its own eigen functions. Okay, so H1 applied to the phi beta produces the energy of the beta state phi beta. So this is an eigenvalue equation, all right? And of course, we have here phi beta as a function of position and time. Of course, as I said, we could plug in the time dependence into the operators. It is no problem in doing that, all right? But now this energy eigenvalue is just a number. And remember, the summation I am just bringing in front of everything, because sum times another sum here, I am having all sorts of combinations of alpha and beta, and it must be summed over alpha and beta. Okay, so now what do we have? This is very general. You could use any given basis. Okay, so what do we have really for now? It is our Hamiltonian in second quantized version, but it's just for a single particle first quantized Hamiltonians. I am not considering yet the interactions between particles. What do we have here is a summation, because I can switch, I can commute the integral with the summation. This doesn't depend on the position. I am able to just insert time dependence here, but of course, not position dependence, because all the position dependence is in the eigenfunctions of the Hamiltonian, of the first quantized Hamiltonian. So this is not dependent on the variables of integration. I can pull them out of the integral. So C alpha dagger C beta, and the energy is just a number depending on beta, and the only position dependent aspects are carried by these functions phi alpha, phi beta. This is dagger phi alpha. Okay, so I need to integrate over the entire volume, over the entire space, phi alpha dagger at the position R, phi beta dagger at the position R. I am just bringing to here the time dependence as I mentioned, so I could make it a function of time, C beta a function of time, just to remove the time dependence from there. It will be no problem, okay? It will be no problem because the only dependence which you could bring for eigenstates of the Hamiltonian, it will be the following. E phi alpha of R and T is just phi alpha exponential of minus I energy alpha times T divided by the H bar. So the position dependence is here and time dependence is here, and you can just add the position dependent, the time dependence. You can multiply by the operators at time t equal to 0, okay? So the time dependence you can put into the functions here or into the operators here outside the integral. But it doesn't matter. As a matter of fact, the result is the same in the end. So let me calculate that integral, okay? What is that integral? But remember, the basis, properties, okay? Phi alpha projected onto phi beta is just the same as inserting the completeness in the position basis. So you can insert the completeness here, phi alpha times r, phi beta. And this is just the integral over the entire volume. Phi alpha dagger of r, phi beta of r. And of course, this is a Kronecker delta. Okay? So this integral is normalized to a Kronecker delta. All right? If you have a discrete set of states, if you have a continuous set, this would be an integral over alpha and beta, but this would be a double integral over alpha and beta, okay? So if you have a discrete set of quantum numbers, it is a countable set, okay? This corresponds to a Kronecker delta. This is a double summation. If this is a continuous, you have a Dirac delta here, and this is a double integral. Okay, it doesn't matter. Okay, result, you can replace integrals by summations, and therefore the job is done also for continuous variables indexing the quantum states. Okay, but for atomic orbitals, if you're considering atomic orbitals which are bounded states, okay, the labels for the atomic orbitals are take values on a discrete set, okay? So it's countable, it is numerable, and therefore you have a Kronecker delta here. If you are considering plane waves, of course, this is a continuous set, and this will be Dirac delta, and the summation will be an integral. It will be converted into an integral here. Okay, so this for discrete, for the discrete case. For continuous of the alpha and beta, it will be a Dirac delta here. Delta of alpha, delta of alpha minus beta. Okay, if you are dealing with a continuous set of quantum numbers. Okay, but now what we have here is just a Kronecker delta. All right. So our Hamiltonian, I will erase here. So our Hamiltonian will be of the following form: H, the Hamiltonian, is a summation over alpha and beta. C dagger alpha, C beta, they are energies. The energy of the state beta, delta alpha beta. This is a Kronecker delta. And when you sum over the label beta, the index beta, fixing the alpha value, what you find out, the only possible result which is non-vanishing is when alpha, where when is beta equal to alpha, when alpha is equal to beta, because of the Kronecker delta. The Kronecker delta came from here. This is the Kronecker delta, and it came from here because it is a property of a basis. The basis is orthonormalized. Okay, so this came from the basis. And when you integrate, when you sum over beta, you need to replace beta by alpha, because the only time when this delta is non-zero is when beta is equal to alpha. So summing with a delta is just the same as removing that summation. You just keep the summation over alpha and replacing beta by alpha. Okay, so you have what do you have at the end? E alpha, because you need to replace beta by alpha. C dagger alpha, C alpha, they are operators, but it is just a number operator. Okay, a second quantized number operator. So what is the result of a second quantized Hamiltonian? It is a summation over alpha, the energy of the state alpha, times the number of particles in that state. Okay, this is your second quantized version of a Hamiltonian for a single particle. For a single particle, you can put your Hamiltonian in a diagonal form, being the number operator, what is your diagonalized operator. So the Hamiltonian is diagonalized in the number representation. And these operators are creation and annihilation operators. The product of the two is just a number operator. You have your second quantized Hamiltonian. Second quantized Hamiltonian for the single particle Hamiltonian, you go to a many particle Hamiltonian where you can put in the energy E alpha state, which corresponds to a set of quantum numbers here, and alpha particles. This is an operator which measures the number of particles there. If bosons, notice we are doing for electrons, but it could be for bosons. So for bosons, the form is the same, okay? The only distinction is that for fermions, given alpha, you can put for fermions 0 or 1 particle at that set of quantum numbers, alpha. For bosons, you could put any given number, 0, 1, 2, 3, or whatever, any given integer into that state if bosons. So fermion is n alpha, if fermion only 0 or 1. Okay, for boson 0, 1, 2, 3, or whatever. This is the only distinction for the single particle, for the Hamiltonian, which is a non-interacting Hamiltonian. You do not have interactions, you just have states for single particles, which now you can just fill in according to the energy levels. You can put one fermion in the state alpha 1 with the energy alpha 1, E alpha 1, another fermion in another state alpha 2 with the energy alpha 2, and so on. And this is just the number representation for non-interacting particles. It can interact with external potentials, but not with another identical particles. Okay, so this is for eventually the electrons are interacting with the external field, the external potential produced by ions, by lattice, okay, which is encoded in the potential energy U of R, which is an operator operating on a single particle coordinate. But since you have solved that problem for a single particle, you have a complete set of functions, the phi alphas and phi betas, okay? And you can expand just by second quantizing the wave function. You just replace the complex numbers by operators, creation and annihilation operators, and your Hamiltonian will become this object here. So this is a very useful way of dealing with problems, and this is the general argument. Okay, so if you have an operator, the Hamiltonian operator in second quantization, if you have a operator, so the first case, operators acting on coordinates of a single particle. Okay, what is the coordinates? It could be position, it could be momentum, it could be anything. But what you do, you just pick up the operator in second quantized form. So this is a second quantized form. You just pick up the operator in first quantization, which is perhaps a Schrödinger operator. You just replace your wave functions by operators. They create particles. You plug in your first quantization operator in the middle of your sandwich here. And the annihilation always there. And in this case, for the Hamiltonian, we already have shown that this is just the summation of number operators, okay, multiplied by the energy of the state alpha, okay, giving a complete set of functions. So for plane waves, particles having spin, your second quantized Hamiltonian, it is not difficult to show that. I showed using a complete set satisfying the properties of a given basis, but if you are using plane waves, you have in the discrete case, these alphas are momentum and spins, the energies corresponding to that momentum and that spin. If you have magnetic fields applied to your system, the spins are splitted in energy, okay, so this energy would depend on the spin of the particle, and this is the number of particles in a given momentum state and spin state, okay, so this is the number operator for a given momentum and spin state. So your labels alpha correspond to a set of quantum numbers, okay, so for plane waves with definite spin, okay, with spin sigma. So in the discrete case, your functions for momentum and spin would be a polyspinor divided by the square root of n, as we discussed in the previous lecture, times exponential of I, a given momentum, times position divided by the h bar. So just to make sense of discreteness, I will label it with a second label pj here. So pj, a given j, you'll find out this form of your wave function. If it is a discrete scenario, you would use for your phi's, depending on the position, something like this. Okay. And of course, the energies, if no magnetic fields, for B equal to 0, for no magnetic fields, your energies would depend only on, usually if you neglect spin orbit, of course, also, you would have something depending only on momentum, p squared divided by twice the mass of the particle, right? I guess you could not see what I just wrote here, but for magnetic fields, zero magnetic fields, so for zero fields, zero magnetic fields, your energies would not depend on the spin. Eventually they depend if you consider spin orbit coupling, but suppose there are no problems with that and external magnetic fields are zero, so for free particles, p squared divided by twice the mass for non-relativistic particles, right? That would be your energy, your set of energy values possible in this problem, okay? So for plane waves, free particles with spin sigma, the Hamiltonian just produces the following thing here, okay? So now let me just remember, suppose you have a particle within a given state alpha, okay? So I'll call this state phi alpha occupied by one particle. So alpha, just use alpha here, okay? One particle in the state alpha, a given a very specific state alpha. When you apply the second quantized Hamiltonian to this state, 1 alpha, and you calculate the average, what you would find, so this state has a one particle in the state alpha and zero particles in other states. Okay, this is the state. There is only one particle in your problem, just one particle overall. What you find out, for any other state, you apply the number operator to this state 0, this state 0, this state 0, because it counts the number of particles. It's a number operator. The only state which is occupied is this one with one particle. What is the energy of this state? E alpha. And you have, therefore, a projection of the state of one particle with the same state with one particle. This is just one because the number representation is also normalized and your Hamiltonian has the energy E alpha. But if you have as many particles, if you have one particle in the state alpha, one particle in the state alpha 1, suppose, one particle in the state alpha 2, one particle in the state alpha 3, and so on, you project out the Hamiltonian just to calculate the average. What you will find out, just a summation over the alphas occupied, the alpha occupied, the alpha which are occupied, you just sum over all the states occupied in the states alpha, the energies of that states. It is just what you need to have for as many particles you have in the system occupying a given set of states. So your average of the second quantized Hamiltonian given the number representation is just the summation of the energies of the occupied states. If fermions, you could only have one and zeros for the states. So a state alpha could be occupied or unoccupied. Okay, but for bosons, the same rules apply, but you would have here the number of particles occupying that state. So if you have three bosons in the state alpha here, suppose they were bosons, you could put two particles in the state alpha and your energy would be twice the energy of a single particle in that state. All right? Let us continue just now calculating things for interacting particles. Okay, so what for? I'll give you the recipe here. What for interactions? So the second case, important case, interactions. So if you have an operator, any given operator, depending on the coordinates of two particles, okay, for two particles, what you do, it is, I will plug in a number 2 here just to remember they are operators which operate on the coordinates of two particles. So this is operator in a first quantization which are applied to the position of the first particle and the position of the second particle. They are operators. Okay. What you do in the second quantized version, this operator is calculated the following way. 1 over 2 factorial, which is 1 over 2, all right? The integral, it becomes a double integral over R1 and R2 in the case of three-dimensional space. They are three-dimensional integrals. If you are dealing with a distinct set of spatial coordinates, it will be a d-dimensional here, but I will use three-dimensional space, which is the most common case, and of course it's relevant. But in two dimensions, you could have a system in a solid state system which is a thin film, okay, so or eventually a quantum wire, right? So one dimensional. But I will use the notation for three-dimensional space. What you do, you just pick up operators in the following order. So this is a creation operator. Let me write it here. So here. So this operator in second quantized, so second quantization of interactions. Interactions means operators act on more than one particle coordinates. And they need to be identical particles. So this acts on the coordinates of electron 1 and at the same time in the coordinates of electron 2. Okay? Right? And they cannot be factorized. Right? Well, these operators corresponding to interactions in second quantized version, you just need to divide it by 1 over 2 factorial. You integrate over the coordinates of the two particles over the d-dimensional space. Okay, so volume integrals over volume of the particle 1, volume of the particle 2, in the entire volume of space, but with respect to the coordinates of particle 1 and 2, and you use it, you second quantize in the following way. So psi dagger of R1, psi dagger of R2, the operator of the second of the two coordinates here, R1 and R2. Okay, so this is the operator in the first quantization, so it's the first quantized operator. So it's the first quantized operator here, and this will be a second quantized operator. Okay, so this is a second quantized operator, and here you just reverse the order. So R2 psi of R1. Okay, so this is the rule. Okay, 1 over 2 integrate over all the coordinates, which are these coordinates of the particles. Psi of R1, psi dagger, this is creation, dagger of R1, dagger of R2. the operator, which we are trying to second quantize here, but depends on the coordinates of two particles, psi of R2, psi of R1. Notice the order. R1, R2, R2, R1. Okay? So the most external R1, the internal indices R2. And this corresponds to the interaction of two particles. Okay? So a two-particle interaction. You could have, it is not usual, but you could have a three-particle, okay, depending on the coordinates of particle 1, 2, and 3. And what you need to do, divide it, it is a recipe, okay? Divide it by 1 over 3 factorial, integrate over all the coordinates of R1, R2, and R3, okay? So you have a psi dagger of the particle 1 is just a very simple notation. It's just R1 here, but usually in the books you could, some books you could find not the entire notation. You just find the one in the argument, but is just meaning that you are integrating over R1. Okay, so 1, and the second particle dagger for the second, there are R2, and the dagger for the third particle, okay, the operator, which in the first quantization acts on coordinates of three particles, and here you go descending the order. So the psi, which is annihilation of particle in the R3 coordinates, the annihilation in the coordinates of the second particle, and the annihilation in the first particles. So 1, 2, 3, 3, 2, 1. Okay, R1, R2, R3, R3, R2, R1. And you can go as many orders you can find. This is a general rule. So 1 over n factorial integration with respect to the coordinates R1, R2, R3, Rn, psi dagger 1, psi dagger 2, psi dagger n. The operator of n particles, you could have R1, R2, R3, R4 to get the Rn. Psi n, psi n minus 1, psi to reach the 1 here, the coordinates of the particle 1. So this will be a set of products of annihilation and creation operators. But notice that this rule always produce something like creation operators to the left, annihilation operators to the right. This is a recipe for doing that. Why is that way? Because when you act first with the annihilation operators in an interaction, you just destroy the initial states, and then you create the final states after the interaction occurred. This is why, okay? But let us calculate for an example here. Let us use one example. And this is a very instructive example. So, of course, for a general situation, all right, for a very general situation, in general, what you would have, your size will be expanded in a given basis, all right? So C alpha, phi alpha, depending on position and time. Time could be put in here, okay? And for your Hamiltonian of two particles, so interaction Hamiltonian, okay? I'll insert the subindex I here, just remember interactions. The second order interaction is the most common in many situations. You have a 1/2 here, so there is a 1/2 because it's an interaction between two particles. You have a potential corresponding to the interaction, so potential energy, which is something like U of R1 and R2. Okay, it depends on two particles. Okay, and then you integrate it over R1 and R2 over the entire volume. Okay, it's a three-dimensional integral, and you would have a psi dagger of R1, a psi dagger of R2, the potential interaction, the potential energy of the interacting particles. So of interacting particles here. And here you'll have a psi of, so this potential here depends on R1 and R2 in some manner. Okay. So psi of R2, psi of R1 here. And now we will use a complete basis. So when we rewrite the interaction Hamiltonian in a second quantized fashion, you need to integrate over R1 and over R2, which are the coordinates of the first and the second particle taking place in the collision or in the interaction, in the scattering. Okay, and here we will write a summation over alpha, C dagger alpha, phi alpha of 1. This one means R1, the coordinates of the particle 1. And I'm just making the notation more clean. Do not write it explicitly R1, R2, because expressions become large. Okay, so this is for the particle, this is for the psi dagger of R1. A second summation, I need to use a second label of which is a set of quantum numbers, beta, C dagger of beta, phi beta of the R2. Okay, so this is operators. These are operators. These are phi daggers of alpha and beta. Okay, this is the potential matrix connecting the two particles. Okay, connecting the particle 1 and 2. So just for the sake of simplicity and the cleanness of notation, we will write in place of R1 and R2 just 1 and 2. Okay, and now I need more indices. Alpha for expanding this is, they are expanding in the same basis, but I need to say that when you need to expand functions and multiply them, always use distinct dummy indices or indices which will be summed over. Here it is the expansion of this part, use a label alpha. For the other, it doesn't matter if the states beta are the same, but you need to take into consideration all the multiplications. And if you use the same single symbol alpha here, you can make confusions. So you need to use alpha here, beta here, another symbol there. Suppose gamma, okay, and lambda, perhaps, or whatever you prefer. So C gamma of and times the phi of the position of the particle 2, so phi of 2, all right, because I am expanding this here, okay. My gamma is not very clear, it seems like an alpha, so I'll use a an index mu. Okay, so mu, and the state is mu here. And I need to expand the last factor, summed over some nu, c nu, phi nu over position R1. Okay, so this is here, this term is here, this term is here. The potential connecting particles at positions 1 and 2. This is expanded here. This is expanded here at the same instant of time. Okay, so time is implicit in the operators. Okay, and now in general, for a second order, what we will have in the end, we will have the following: a Hamiltonian, which corresponds to interaction between two particles. It is given by a summation over alpha, beta, mu, and nu, because there are alpha, mu, and nu indices. C alpha dagger, C beta dagger, C nu, C nu. Okay, they are just operators. They do not depend on position. The dependence on position, which are being integrated, occur here in the basis functions and in the potential. So you will have an integral which is a double integral over R1 and over R2 of something like phi alpha dagger depending on the position 1, phi beta depending on the position of the second particle. They are the daggers. The potential u of 1 and 2, phi nu of the particle 2 and phi nu of the particle 1. Okay, so this is an integral which you need to perform given the potential. Okay, and this will produce something like, I will call it u tilde of alpha, beta, mu, and nu. It connects the states alpha, beta, mu, and nu. This is just now a number because you integrate out these things. This produces a number, and the result for the Hamiltonian in the second quantized version is the following: an interacting Hamiltonian for two particles would look like the following thing: alpha, beta, mu, and nu of some number here, depending on the states, alpha, beta, mu, and nu, C dagger, C dagger, C dagger alpha, C dagger beta, C mu, and C nu. Okay, so this is what results. And this four operators product, what does that really mean? Okay, there is a way to represent that, which is known as Feynman diagrams. It is a way to represent things, and when you have a second quantized Hamiltonian, they are very intuitive. What you have here, you have a initial state mu, okay, which corresponds to a set of quantum numbers for an initial particle nu, and you have a particle with quantum numbers mu. So suppose they are electrons, they will correspond to the initial states mu and nu. It could be plane waves, okay, free electrons. When they see each other, they collide, they interact here, okay. The interaction is this matrix element alpha, beta, mu, and nu, okay. And in the end, what emerges? A state beta here and a state alpha here, okay. Or you can switch them because they are identical particles. All right. So suppose you have a particle, an electron in the new state. This state will be destroyed when the particle collides with an electron in the new state. These initial states disappear. The amplitude of the interaction is produced by this integral, okay, and emerge from the scattering the particles in the quantum states alpha and beta. But what produces alpha and beta? I don't know. I am zooming over. Okay, I am zooming over. Given the set of quantum numbers corresponding to beta here and alpha, well, at some point in the summations here, you will have the reverse order. And for bosons, the switching of quantum numbers produces nothing. And for fermions, the exchange of the numbers produces a minus sign, okay, because they are fermions, all right? But you need to calculate this integral, and you'll find out something like a graph representing the interaction. So this, suppose the time axis is to the right, okay? So a first particle, a two particle state is destroyed in the interaction and emerges after they scatter two final states, okay? With interaction, which is mediated by, I don't know, whatever, because it could be electrons, it could be any other kind of particle, it could be bosons, all right? So the form of the Hamiltonian for a second order interaction is the same, okay? But these operators for electrons, they are fermionic operators satisfying fermionic algebra. For bosons, they are bosonic operators satisfying bosonic algebra. And the Feynman diagram just corresponds to making a plot or a graph. It is a graphical technique which allow you to just see in an intuitive way what is happening here. So what is happening here is that you are producing a scattering, which before the interaction, electron 1 or electron nu are in this state nu, and electron mu is in this state mu with quantum numbers mu. And when they collide, they scatter to the states alpha and beta with an amplitude given by this integral. Okay. Well, so this is a recipe. A three particle interaction would produce something like a matrix element depending on alpha, beta, gamma, mu, nu, delta, C dagger alpha, C dagger beta, C dagger gamma, C mu, C nu, C delta. Okay, and the summation runs from all the states, but there are 6 summation symbols here: alpha, beta, gamma, mu, nu, if you have a three particle interaction. But it's not usual. So for its third order, perhaps graph. Okay, so for a third order graph, you would have 6 operators, being 3 creation operators, 3 annihilation operators. What I'm using here is the scenario for a single type of particle. The particles interact with each other by some form of potential. Okay? Now, let me show you. We will use this for the case of Coulomb interactions in the next lecture. But let me finish this by calculating equations of motion for the operator. for an operator psi of r and t. So since this is an operator, it must satisfy some equation of motion or some equations of motion. Okay, and since operators evolve in time according to Heisenberg equations of motion, you would calculate using Heisenberg picture. Okay, you need to use the Heisenberg picture to calculate this thing. Okay, so for the sake of simplicity, you could calculate the Hamiltonian of the following form. Suppose in second quantized version, you have an integral over the entire volume, the part which corresponds to a single particle. So you have an Hamiltonian for a single particle here, psi of r, of course, and t, psi of r and t. Let me use here an index 1, so psi dagger of r1 and t, the Hamiltonian for a single particle here, psi of r1 and t, and plus 1 over 2. Suppose you have a second order interaction, an integral over r1, an integral over r2 over the entire volume, psi dagger of 1. Let me use the condensed notation. For r1 I will use 1, so 1 psi dagger of 2. Time is implicit, okay? It depends on time, and the Hamiltonian is calculated with all the wave functions at the same time, okay? So this is for the Hamiltonian. Psi dagger of 1, psi dagger of 2, a second order interaction, so I will use the letter U here, the capital U. It depends on R1 and R2, psi 2, psi of 1, coordinates 1 and 2. So 1, 2, 2, 1. Okay, this is what we need to do. So since this is an operator, of course, Heisenberg states that I h bar, the derivative of an operator, which is now the psi hat. Okay, this is an operator depending on the position r at the instant time t, is equal to a psi hat of r and t commutated with the Hamiltonian. What Hamiltonian? The second quantized Hamiltonian here. Okay, so this is the equation of motion. Of course, you can calculate that for the psi dagger, which is the transpose conjugated of this equation. Okay, it doesn't put any major problem to do that. But now I need to consider what are the particles to calculate that, if they are bosons or if they are fermions, for making the whole calculation. Okay, so we have two terms in the Hamiltonian. This is the part which you do not have interactions, and this is the interacting part. So let me calculate the first part in the first case. So we have for this part here, okay, and of course we need to calculate the second part, but just to show you what happens, we have to calculate the commutator of psi of r at the instant of time t, commutated because it is the right hand side, which is the problem here. We need to calculate the commutator. So the commutator includes, for this term here, d3 of r1, psi dagger of r1. This h1 acts on the position R1, okay, and it is being integrated over R1, psi of R1, okay, and we need to commutate this object, okay. So since this is an operator acting to the right on this function here, okay, I will neglect for the moment. I will calculate the commutator with this term first, okay. So what we need to do really is I can, since this is calculated in the position R and this is being integrated in R1, I can change places. I can commute the integral here and rewrite this as the commutator of psi at R and T with psi dagger, it's an operator, at R1, the Hamiltonian, the same instant of time here, okay, Hamiltonian of one of first quantization here. This is a differential operator, okay. And now I can use a following rule. Suppose I have fermions, okay. So for fermions, what I need to do, I need to anti-commute a psi of R and T with psi dagger of R1 and T, and this is an object which is the you need to use the rules for ABC, commutators of A with BC, and you need to expand this as anti-commutator of A and B times C minus B, anti-commutator of A and C. Okay, this is the rule which you need to use. If bosons, commutator, commutator, a plus here, okay, and commutator is here. But since they are fermions, we are using the example of electrons. We use anti-commutators, and this is the first part here. The second part is minus the B, which is this thing here, psi dagger of R1. It is no problem. I cannot switch the H1 with any other thing, but since I will have a commutator of psi of R with H1 applied to psi of R1, and this acts only on R1, I can insert the H1 here in front of that commutator because it only acts on the variable R1, okay. So I can do that because the derivative of A and B with respect to some variable, it is just A, the derivative of the second one, since the A doesn't depend on that variable. So A is constant with respect to X. Okay, so this is a differential operator. It is a first quantized operator and the second quantized following rules of bosons or fermions, in this case fermions. It is embedded in these objects, the psi's. Okay, so this H1, it would appear here acting on psi of R1, but there will be products of psi of R, H1, psi of R1, and then this is a differential operator. I can pull in front of everything, so I can use this fact here. I can just place the Hamiltonian for one particle in front of this anti-commutator, and I can close here. So I have this thing here. And remember, for fermions, a commutator of size, suppose here is psi of R and this is psi of R primed, this is 0. Of course, the anti-commutator of psi daggers is also 0, okay? But the anti-commutators of psi dagger, psi with psi dagger, calculated at the position R and the position R1 here, okay? Because that's what we have here. This is psi dagger of R1, okay? Psi dagger with psi dagger of psi with psi dagger of R1. It is just the Dirac delta in 3 dimensions, in this case, of R minus R1. Okay, this is a 3-dimensional delta, Dirac delta. Okay, so this is 0 here. This is 0. And here, what do we have? We have a Dirac delta. So this is a Dirac delta of R minus R1. And now we can use the rules for integration of functions with the delta function. And this commutator of psi of R and t with the integral of d3r psi dagger of 1 h1 psi of 1 coordinates r1, it is just equal to the integral over d3r delta of r minus r1 because of this anti-commutator here. This h1 is applied to the variables r1, and this psi here is the psi which comes with r1, okay? So psi of r1. And the Dirac delta, when you integrate out, is just to replace the variable of integration, which is r1, okay? Which is r1, by the value which makes the argument vanish. So r minus r1 equal to 0 corresponds to replacing r1 by r, and you can eliminate the integral. So this produces Hamiltonian 1 applied to psi of r1, of r, sorry. The Hamiltonian of one particle, which is calculated with respect to position of the particle r1, but now it's calculated with respect to r, and this is it. This is what we have found. So suppose there are no interactions for a non-interacting problem. Suppose there are no interactions. What you find out is that I h bar, the derivative of the operator with respect to time, is equal to the Hamiltonian 1 applied to psi of r and t. This is, of course, r and t. And this looks like Schrödinger's equation. So Heisenberg's equation of motion for the operator psi would produce an equation which has the same form of a Schrödinger equation. And this Schrödinger equation, if you expand your problem in terms of a given basis, suppose you can plug in the time dependence over here, okay? You plug in the time dependence in the basis functions. This is the annihilation operators. What you find out is I h bar, since the time dependence is there, you have a C alpha, the time derivative of the phi alpha dt. This depends on space and time. And the h1 will be applied to the phi. So you have a summation over alpha here, a summation over alpha there. C alpha, it's an operator. The h1 is applied to phi alpha of r and t. Since the operators can be considered as directions in some abstract space, what you find out is that this produces the following equation. I h bar, the derivative of phi alpha, over dt is equal to h1 applied to phi alpha, and this phi alpha can be rewritten as a function of position only times e to the minus imaginary unit e alpha times t divided by the h bar, which produces the original equation, which is energy alpha times phi alpha of r is equal to h1, the Hamiltonian of one particle, applied to the eigenstate, the eigenfunction corresponding to that eigenenergy. Okay, this is what the second quantized equations of motion produce for any given state. It is it. If, on the contrary, you want to put the dependence on the c's here, you'll find out if you're not considering the time dependence in the states, this exponential here will be appearing in the c's. So c alpha of t would be given by c alpha e to the minus I e alpha t divided by the h bar. If you eliminate the time dependence from the basis functions, they will appear in the operators. If, on the contrary, if you consider the operators as at the same at time t equals to 0, the time dependence will be enforced on the basis functions. But whatever you choose to do, it will look like a Schrödinger equation for operator psi. Okay, you started with Heisenberg equation of motion. The Heisenberg for an operator produces something like which is a Schrödinger equation like, and this produces a Schrödinger equation for the phis. Okay, if you consider the second order, you need to consider that. Okay? Consider second order interactions. Considering interactions, what you need to do, you need to calculate this thing here, psi of r at the same time t, the commutator with the second part of the Hamiltonian, which is integration over coordinates r1, coordinates r2, and this will be 1 over 2 factorial psi dagger of r1, which is just denoted by 1, psi dagger of 2. They are operators. The interaction element of particles 1 and 2, psi 2, psi 1. Now you have a very complicated issue here because you have to calculate something like commutators of A with B, C, D, E. Okay, 1, 2, 3, 4 matrices with one matrix here. Operators, okay? So you need to calculate something like that. It is better to use some strategy here. I will not do it here, but I guess you can find the solution for this problem in many books. But I guess in Field Quantization by Grainer. But it just produces what is called the Hartree-Fock equation. It is equivalent to the Hartree-Fock equation or approximation. Okay, produces something like the Hartree-Fock approximation, which is a solution for a system of interacting fermions. Of course, you can consider for bosons too. All right. Well, uh, I will finish this here. We need to discuss in the next lecture. We need to discuss the case of the Coulomb potential or the electrostatic potential, the Coulomb interaction between electrons, which is a very important case. And after that, just remember, we already have a Hamiltonian for non-interacting particles, which is an important scenario in many cases. We have the energy of the states alphas times the number operators. It is valid for bosons or fermions, for non-interacting bosons or non-interacting fermions. This is a free case, free particles, but you also have eventually the interactions here. So some U's, okay, with C dagger, C, alpha, beta, lambda, delta here. You have operators, products of operators. So these are interactions. Okay, and this is very important. In next lectures, we will need to introduce, after we discuss the Coulomb interaction, we need to introduce the density matrix and calculate the statistics for fermions and bosons, the quantum statistics. We will arrive at Fermi-Dirac distribution for fermions, Bose-Einstein distribution for bosons, and I'll see you next time. Bye bye.